Lesson 4.2, Gaussian Elimination. Okay, class, we worked, last time we worked with a real quick example of Gaussian elimination in two variables. We're going to expand that to three variables, and we're going to do a couple of examples here to get you prepared for doing your the discussion problems. Okay, so here's our example. We have x, y, and z. Now remember what we mentioned before, that if you have three unknowns, you have to have three equations constraining them. Now, if you think about that for a moment, if we were to just multiply this first equation here by 10, so it would be 10x plus 10y minus 10y plus 20z equals minus 30. Okay, that's not really a different relationship between those variables, and that's what we would say, that it's not a linearly independent. Now, are any of these sufficiently related that they don't actually constrain the values of x and y? We don't quite, x, y, and z. We don't really know yet, okay, but let's work through it. Now, as I've said in the past, the key to getting good at math, or really anything, is to make a lot of mistakes, but make them only one time. One thing that's helped me to not make mistakes with Gaussian elimination is to number my equations. Now, the first time we come up with an equation, the first time we see it, I'll go ahead and I'll put that in red text just so it stands out. After that, I'll just use the black text. Okay, so we have three variables, x, y, and z. We have three equations. Hopefully that they'll provide enough constraint that we can come up with a unique solution. But you've got to keep in mind that perhaps no solution is actually the solution you'll be looking for. Okay, Gaussian elimination depends on the idea that if we multiply all the terms of an expression by the same factor, we don't change the solution. So y equals x plus 1 and 10y equals 10x plus 10 both represent the same line. The same line on a graph. Okay, so let's take our equations. Oh, wait a minute, I used the red text several places. Okay. So let's go ahead and let's take our first equation. X minus y plus 2z equals minus 3. I'm going to multiply the equation by minus 1, and I'm going to add it to equation 2. Now, equation 2 is x plus 2y plus 3z equals 4. Now, you might ask yourself, why did I multiply it by minus 1? Well, I multiplied it by minus 1 so that when we add these two equations together, we're going to add all of the x terms together, that this is going to sum to 0. So we're going to come up with a new equation, an equation 4, that does not contain the variable x. All right. And in the same way, we're going to multiply equation 1 by minus 2 and add it to equation 3. Here we added it to equation 2. Now we're adding it to equation 3. Okay, so here's the first equation times minus 2. And we run through and we find that we have two equations, equations 4 and equation 5, which do not contain the variable x. So we have eliminated x from there. Now, we can just simply add equations 4 and 5. So 3y plus z equals 7. We're going to add that to minus 3y plus 3z equals minus 3. Now you can see why I reverted back to the version of equation 5 with the multiples of 3, because even though you can reduce it to this, it was just more convenient to be able to add those together. Okay, so 3y minus 3y is 0. We know that our expression is going to contain only one variable. 4z equals 4. So plus z and plus 3z is 4z. 7 minus 3 is 4. So we have 4z equals 4 and z equals 1. So we can go back to equation 5 and obtain with z equal to 1. So y minus 1 equals 1. We can see that y is going to be equal to 2. going to go back to equation 1. We're going to evaluate equation 1 with y equals 2 and z equals 1. So x minus y plus 2z equals 3 is equal to x minus 3, because we're going to maintain that same factor there, minus 3, plus y. Remember, we've moved it across the minus, the equality, so in order to get rid of it here, we have to add plus y to both sides. Plus y minus y summed up is 0. So plus y on this side. And again, if we have plus 2z, we're going to have to subtract it from both sides in order to get that factor over on the other side of the equation. So minus 2z, and we're going to substitute in our solution. Y equals 2, z equals 1. We're just going to go ahead and evaluate that. Turns out that x is equal to minus 3. So our solution then is minus 3, 2, and 1. It turns out that these equations represent planes in the coordinate system. That's not our originals. That these equations represent 3 planes that intersect at a single point. And that single point that we found was minus 3x, 2y into y, and 1 into z. Well, good luck. Oh, we have another example. Here's our system of equations. We have 3 equations, 3 unknowns. There's the potential to being able to solve that. We're going to add equation 1 into both equations 2 and 3. And if you take a look here, what we're going to be doing is we're going to be using that minus z. We're going to eliminate z first. So if I add this one and this one, z goes away. So let's do that. So equations 4 and 5, okay, 3x plus y equals minus 4. 9x plus 3y equals minus 6. I'm going to multiply 3 times equation 4 and subtract it to equation 5. Because we have like 3x here, and then we're going to want to get rid of x, so we're going to multiply this one by 3, or minus 3. Okay, so 9x plus 3y equals minus 6. We just transfer that down from here. This is a version of equation 4. Minus 9x minus 3 equals 12. And now we can add those together, and we see that, oh, wait a minute, there's a problem. By doing so, we got rid of all of our variables. It turns out that 0 equals 12 is not true. And thus, in this second example, I wanted to give you an example of a system of equations that did not have a solution set. Okay.